What's up, team? Today we're talking about inverse trig functions, inverse trigonometry functions. You see the learning target right here. I can solve right triangles using inverse trig functions. So what's going on here? Let's review inverse, like just what that means in the context of math real quick. So I have these listed here. I have 5 squared is 25. 5 to the first power is 5. 5 to the 0th power, you may not remember this, but it is indeed 1. Anything to the 0th power is 1. And then we get to the negatives. This is where it gets a little bit weird. 5 to the negative first power is 1 over 5, and 5 to the negative second power is 1 over 25. You see some symmetry here. As we go out from 5 to the 0th power, we have 5, and we have 1/5. If we keep going, we have 25, and we have 1 over 25. So the 5 to the first power and 5 to the negative first power, we say are inverses of one another because we're doing the opposite thing, essentially. Let me do one more quick example to illustrate this point. 10 times 5 is 50. All day long, no surprises. Well, what if we do 10 times 5 to the negative first power, the inverse of 5? Let's break down what that means and what's going on here. So 10 times 5 to the negative first power is the same thing as saying 10 times 1 over 5. And again, this 1/5, it's the same 1/5 that we're talked about over on this side. But 10 times 1/5, that's really the same thing as 10 divided by 5, which would end up equaling 2. So what I'm trying to illustrate here is when you have some number, some value, some anything, it doesn't have to be 5. It can be anything. If you have that number and then you have the inverse of it, really what's going on is we're just doing the opposite thing, I suppose, is the simplest way to put it. So when it comes to trig functions, we've been studying these functions. If we have the angle measure, we can then find a missing side using sine, cosine, and tangent. What we're going to learn today is, well, what if you have the sides, but you don't have the angle measures? So we're going to use the inverse trig functions. So the ratios are the same idea, it's just kind of the opposite of one another. Just like 5 is still 5, but if we take the inverse of 5, it's like we're dividing by 5 instead of multiplying. It's the same kind of idea. So don't let that little negative one scare you. I'm going to do my best to make it make the most sense as possible here in a moment. Okay, I got a conditional statement for you. If the sine of 30 degrees equals 1/2, so the ratio, if you have an angle of 30 degrees, the sine of that, the opposite over the hypotenuse is 1 over 2. Then the inverse sine of 1/2 is 30 degrees. So all that happens here is that the angle measure and the ratio, they flip places when we take the inverse function there. It's how we use this. So don't worry, you're going to get a ton of practice. That should seem weird to you right now. So when would we use one? When would we use the other? Good question. So here's the situation here. This is kind of like what we worked with last time in our last lesson. We have some triangle, we have a 30-degree angle, I've named it A, the opposite side has a length of 6, and the hypotenuse is what we're chasing. That's our goal. So we could set this up. We could say that the sine of 30 equals the ratio of the opposite over the hypotenuse. So that's 6 over x. And then from here, we can multiply both sides by x, and we could solve. This is what we've done already. So this is when you would use the standard sine or the standard trig function. Well, when would you use the inverse trig function? That would be a situation like this one. If this is the same exact triangle, we just know different pieces about it. In this case, we have our angle A, but we don't know the angle measure, but we do know the ratio of the opposite to the adjacent angles. So we'd set this one up. We know that we know that we have the opposite and the opposite and the hypotenuse here. So it's going to be a sine function. But in this case, we don't have our angle measure, so we're going to say it's an inverse sine function. And here's how we're going to set it up. We're going to say that the sine, we can take an extra step here. The sine of A equals 6 over 12. Sine of A equals 6 over 12. Of course, you can reduce that to 1/2. Well, we can't just solve it like this, so we're going to use our inverse trig function and say that the inverse sine of 1/2 equals A, or the measure of angle A in this case. So the inverse sine 1/2, that came from 6 over 12. And when you plug something like this into your calculator, the inverse trig function is always going to have a ratio in parentheses, whereas the typical trig function is always going to have your angle measure. And then the flip-flop is true as well. On the outside, you're going to have your ratio, and over here, the outside, you're going to end up with your angle measure. And I should have written this as the measure of angle A, to be just a little bit more precise. Okay, let's bounce over here. I have some more conditional statements. If you're going to write something down, this is what I would write down. Let's make sure it makes sense for us, though. So this first one says, if the sine of A equals x, x is some ratio, A is some angle measure, then the inverse sine of x, so the inverse sine of that very same ratio, equals the measure of angle A. The same is true for the cosine of B. If the cosine of B is y, yeah, the cosine of some angle measure is some other ratio. Well, then if you flip those around, the inverse cosine of that very same angle measure, the very same ratio equals the original angle measure. And tangent, same thing, I just changed the letters to C and Z. Okay, I want to do a little bit of practice with our calculator, and then I'm going to do a big example why we would use inverse trig functions. So I have some inverse trig stuff up here. I'm not going to walk through each of these. Go ahead and pause the video. Make sure you know how to use your calculator. That's why this is here. So if you type in the inverse sine of 1/2, your calculator better spit out 30. Same thing with the inverse cosine of 1/2, it's 60, etc. It might be in the wrong mode. Make sure there's a little DEG somewhere on there. Your calculator should be in degree mode, not radian mode for these. If you're having troubles and you're not able to figure it out, shoot me an email, ask me in class. But I am going to move forward to our example at this point in time. Okay, here we go. One big problem. We have triangle ABC here. We have a side length of 33, a side length of 65, and our task is to solve triangle ABC. That's new language. Solve a triangle. Well, what does that mean? It means that we're going to find all 3 angle measures. We're going to find all 3 side lengths. So far, we have 1 angle measure, 2 side lengths, so we have 3 of the 6 required pieces of information. Our task is to find the other 3 pieces. Let's dive in. We are going to start by finding first the measure of angle C. You could start with the measure of angle A. Sure, you could totally do that. Another way you could start is doing Pythagorean theorem and finding the hypotenuse. I'm not going to mess with Pythagorean theorem today. Of course we can do it. Of course we know how. This lesson is focused on trig, so we're going to get some trig done to find that hypotenuse length. So I want to start first by finding the measure of angle C. That is our first task. It's right here. We know from the perspective of angle C that we have the opposite leg length and we have the adjacent leg length. So we can set up a trig function. We can say that the tangent of angle C equals opposite over adjacent. Okay, so this is a true statement, but it doesn't quite get us where we want to go because we can't plug tan C into our calculator. Our task is to find C in this case. So we're going to use the inverse trig function. Essentially, we're taking the inverse of both sides here. So we're going to say that the inverse tangent of our ratio equals the measure of angle C. So essentially, if you're thinking like algebra stuff, we did the same thing to both sides. We took the inverse tangent of here, which canceled out the tangent, and we're left with just C. Took the inverse tangent of this ratio, and we put it in here, and of course, we just flip-flop the sides. Okay, at this point in time, plug that business into your calculator. It's the inverse tangent of 33 over 65. So if you have a TI-30, which I highly, highly, highly recommend, you're going to press second, you're going to press the tan button, and then we're going to plug in our ratio, 33 divided by 65, boom, and we learn that this angle measure is 26.9, 26.92 degrees. Boom. So C, the measure of angle C is 26.92 degrees. That piece is done. We now have 4 of our 6 required pieces. Let's do the same thing for the measure of angle A. So the measure of angle A now. That is our task. We can do really the same thing, just different. Opposite over adjacent. So the measure of angle A. So we could say the tangent of A equals opposite over adjacent, 65 over 33. But of course, again, we can't plug tan A into our calculator because our calculator does not know what A is yet. So we're going to take the inverse tangent of both sides. So we'll go tan inverse our ratio. This time it's 65 over 33 equals the measure of angle A. So here we go, back to the calculator. Pressing second, tangent. So I have the inverse tangent up here, 65 divided by 33, close my parenthesis, boom. This angle measure is 63.08. 63.08 degrees. So the measure of angle A equals 63.08 8 degrees. I don't know why I boxed that. That is what we found there. Okay, this makes sense because if we look at these two angle measures, they are complementary to one another. They add up to 90 degrees. That's great. That means all three of these add up to 180. That is a big, big win. Now, we need to find this hypotenuse. I'm going to use this side of the board over here. Find AC in this case. Here we don't need to use an inverse trig function. We have enough information. What I'm about to do, we could have done during the last lesson. So we have choices. We can either come at this from the perspective of angle A or C. We're going to use a sine or a cosine function, thinking SOHCAHTOA. We need to involve the hypotenuse here. So there's 4 different correct ways we can take this. I'm just going to start at the top. So I'm going to use angle A, and how about I use the 33 because it's smaller than 65. So if I use the 33, that's the adjacent side to angle A, and I'm aiming to find the hypotenuse. Adjacent hypotenuse means cosine of our angle measure, 63.08, equals adjacent over hypotenuse. A little bit of algebra 1, I learned that x times the cosine of 63.08 equals 33. One more piece of algebra, divide both sides by this cosine business, and I learned that x equals 33 over cosine of 63.08. Bust out our handy calculators. Again, I'm going to show you how to do it on the TI-30. I type in 33 divided by cosine of 63.08, close my parenthesis. Boom, our side length is 72.89. 72.89 degrees. And that seems to make sense because this is indeed bigger than both sides. I'm willing to bet if we were to use Pythagorean theorem, that's not degrees, not an angle measure, just a side length. I'm willing to bet if we use Pythagorean theorem, a squared plus b squared, it would equal c squared. I'm not going to take your time in this video, but you can check me if you'd like. Okay, inverse trig functions. Here's one big example. Check my notes, check the solutions that I've posted. If you have any more questions, let me know. I believe in you.